Okay, so what we want to talk about now is something called the addition rule. And in terms of probability, this is actually the last rule we're going to cover, and next we're going to go into discrete probability distributions. All right, so what is this addition rule? All right, well, but to get started, the first thing we need to talk about is mutually exclusive events. So what does it mean for two events to be mutually exclusive? Well, what that means is that events A and B cannot occur at the same time. Okay, so they cannot co-occur. So it cannot snow and be 80 degrees at the same time. Snowing and 80 degrees would be mutually exclusive events. And in probability, what we're saying is that the and probability, the intersection of A and B, so the probability of A and B, is equal to 0. Okay, so in terms of our Venn diagram, what this is saying is that there's no overlap. There's event A, there's event B, and we see that there's no events in that A and B space. So here in this Venn diagram, you're looking at an example of mutually exclusive events. All right, so let's consider a couple examples. So are these events mutually exclusive or not? All right, so it reads, randomly select a nursing major, randomly select a male student. So here's what you ask yourself. Can a randomly selected student be a nursing major and a male? And hopefully what you're saying is absolutely, of course. And so they are not mutually exclusive, okay? Because clearly we can have a student that is a male and a nursing major. All right, let's consider this example. Randomly select a vehicle that is a Ford, and you randomly select a vehicle that is a Toyota. So, what do you think? Well, here, this is an example of mutually exclusive. Why is that? Because we cannot have a car that is both a Ford and a Toyota. A car is going to be one or the other, right? All right, and so one trick here when we think about mutually exclusive is that brands are always mutually exclusive, meaning you can't have a shoe that is both a Nike and an Adidas. It's going to be one or the other. Okay, so brands typically are mutually exclusive. Okay, so now that we have discussed mutually exclusive, we can talk about the addition rule. So what is the addition rule? This is when you're going to read the word or. Okay, so the probability of A or B. All right, and our formula for this is that if we want the probability of A or B, we're going to add the probability of A and the probability of B, but then we're going to subtract the probability of A and B. All right, we need to subtract that intersection. Okay, if A and B are mutually exclusive, then it's simply the probability of A or B is just the probability of A plus the probability of B, because we know that intersection space is equal to 0. There's no intersection. Okay, so let's think about this. Folks, right now, look at your square of non-mutually exclusive events. Okay? So let's make sure that you logically understand this formula. So if we want the probability of A or B, then we add that circle for the probability of A, and then we add that circle for the probability of B. But notice when we do that, we count that purple space twice. So that is why we have to subtract out that intersection once. So again, we add A, we add B, and we have to subtract out the intersection because it gets counted twice. If events are mutually exclusive, as we see in the square on the left, then there is no intersection. We simply just add the probability of A plus the probability of B. All right, so let's do some classical examples. You select a card from a deck. What is the probability the card is a 4 or an ace? Well, the first thing we want to do is ask ourselves, are 4s and aces mutually exclusive? What do you think? Yes, because a card cannot be a 4 and an ace, right? There's no such thing as a card that works as both a 4 and an ace. All right, so these are mutually exclusive. Since they are mutually exclusive, the probability of a 4 or an ace is simply the probability of a 4 plus the probability of an ace. All right, can we calculate these probabilities? Absolutely at this point. We've got 4 over 52 plus 4 over 52. Again, why? Breaking it down, there are 4 4s in the deck out of 52 total cards, and there are 4 aces in the deck out of 52 cards. We add these fractions and get 8 out of 52. All right, and of course, you know, if you want to convert that to a decimal or a percent, we certainly can. All right, let's do another example. You roll a die. What is the probability you roll a number less than 3 or an odd number? Now, again, we start out. Are these events mutually exclusive? All right, so is there any number that is less than 3 and odd? What do you think? Of course there is. All right, so these events are not mutually exclusive because the one face, the 1, is less than 3 and odd. All right, so we've got the probability of a number less than 3 or an odd number is equal to the probability of a number less than 3 plus the probability of an odd number minus the probability of a number less than 3 and an odd number. All right, so what do we have? Let's take a look at our first fraction. How many faces are less than 3? Well, there's 2 of them. So 2 over 6 is our first fraction. How many faces are odd? Well, the 1, the 3, and the 5 are odd. So that gives us 3 over 6 for our middle fraction. And then how many were less than 3 and odd? And we said the 1. So that's 1 over 6. So we've got 2 over 6 plus 3 over 6 minus 1 over 6, giving us 4 over 6. A card is selected from a standard deck. Find the probability that the card is a face card or a heart. So again, we start out. Are face cards and hearts mutually exclusive? What do you think? Are there any cards that are face cards and hearts? Absolutely. So these events are not mutually exclusive because there's a Jack, Queen, and King of Hearts. All right, so what's our formula going to be? We've got the probability of a face card or a heart is equal to the probability of a face card plus the probability of a heart minus the probability of a face card and a heart. All right, so what is our probability of a face card? Hopefully you can recall there are 12 face cards out of 52 total cards. There are 13 hearts out of 52 cards. And then we just said we've got the Jack, Queen, King of Hearts in our intersection. So we have to subtract out those 3. So we've got 12 over 52 plus 13 over 52 minus 3 over 52, giving us 22 over 52. All right, let's transition over to some empirical examples. And again, you're going to definitely see something like this, a contingency table on your quiz as well as on your exam. I can't stress enough, I really enjoy testing with these because I can just ask every single type of probability with a simple table. So what do we have here? We've got RH factor, positive and negative, by blood type, O, A, B, and AB. And we've got 409 individuals in this table. All right, and let's just consider some different types of questions. All right, so find the probability that the donor has type O or type A. Now, is type O and type A mutually exclusive? And the answer is yes. A person cannot have type O and type A blood. So when you're looking at a table, the trick is that columns are mutually exclusive with one another, and rows are mutually exclusive with one another. So here I'm asking you about the probability of 2 columns. So O and A would be mutually exclusive. So we've simply got the probability of O plus the probability of A, which is 184 over 409 plus 164 over 409, and we can add these fractions to get 348 over 409. All right, what about find the probability that the donor has type B or Rh negative blood? Now, is there such a thing as having type B and Rh negative? And the answer is yes. All right, so these events are not mutually exclusive. All right, and we can see that because I have colored that cell blue. Those 8 people are negative and type B, right? That's the overlap. All right, so since they are not mutually exclusive, we need to take the probability of B plus the probability of negative minus the probability of B and negative. All right, so what is our probability of B? We've got 45 over 409. What's our probability of negative? We have 65 over 409. And then again, that blue cell, that 8, has been counted twice. It's in the overlap. So we have to subtract out 8 over 409, giving us 102 over 409. All right, let's go back to, let's just revisit old types of probabilities. So just to keep hitting it home in your head, all these different probabilities that I can ask. So find the probability that the donor has type AB given the donor is Rh positive. Now recall, this is given something. So this is the probability of the second event in a sequence. Something has already occurred. What has happened is Rh positive. And so that is why I have colored that row pink, because we're stuck on it. All right, so we're going to make our probability from that row only. So we look at our AB total and we look at our subtotal on positive, all right, to get our final probability. So our numerator is the number of AB and positive, and we see there are 12 people there. And our denominator is the number positive. So we've got 12 over 344 as our final probability. All right, find the probability that the donor has type A and is Rh positive. All right, so here the probability of A and positive is simply how many are A and positive. We see that with the pink cell, that's the intersection. That's 139 out of the 409 total. Okay? So again, when it comes to the table, I can't stress enough, the AND probability is very simple. We just are really looking at one cell divided by everybody.